So let's say we had a more complex type of model. So let's say the data was in this form, and just a simple line is not complex enough to be a good regression model for the data set that we have. So I just give you some examples. Let's say the model that we have is not even, the basis functions are not polynomials. Let's say you have theta 1 e to the power of x plus theta 2 sine of x plus theta 3 cosine of x. Okay, so here, this is still a linear regression model, even the basis functions are not. Yeah, so that's an important distinction. So here, e to the power of x is a nonlinear basis function, but you see that theta here shows up linearly. So the power of theta is 1, and so it shows up linearly. And, or let's say this is one model. Let's say another choice for the model would be, let's say I use polynomial. I use polynomial of order 100. So that means I'll have 101 parameters, right? So let's say we chose this model or that model, and we want to find the optimal theta. Here now, theta is has only 3 components. Here it has 101 components. So how do we find theta here? So we can again go back and formulate this versus the loss function the way we had it before. We can see here that it mathematically becomes tedious to formulate and write the equations in that form. So if you write here, for example, for the second examples here, you have to write the function versus theta 1, theta 2, theta 3, all the way to theta 101 equals to, and here there is one summation for data points, one summation over data points, 1 over n, the same as before. But here now, for f of x and theta, we have to plug in this huge expansion here. So I have to have theta 1 plus theta 2 xi plus, you can see it becomes, and then minus yi to the power of 2. So now, if we want to find the optimum theta here, we have to derive expressions for del E, del theta 1 equal to 0, del E, del E del theta 2 equal to 0, and all the way to del E del theta 101. So then one has to derive these one by one. Obviously, that's a tedious task, and the basis functions are not polynomials that we derive these universal derivations. Sometimes they could be different functions, and so we want to adopt a different language, mathematical language, so we can see through all these examples, because they all have the same unifying mathematical principle. And so we want to formulate these problems in a unified way, so that we can take these derivatives easily, we can solve these problems easily, we can, and also more importantly, we can code them up in the computer program, MATLAB, Python, whatever language you want to choose in a nice and elegant way. So that's really the objective of this lecture. Okay, so the way we would do that, we're going to use linear algebra, so a lot of linear algebra. So I want to reformulate all of these problems using the language of linear algebra. So we have to introduce new notation. Okay, so in the past lectures and up to this point, I use theta as the vector of theta. Here, because we're going to use a lot of matrix and vector, I want to distinguish between vector and a scalar and matrices. So if something is scalar, I'm not going to put an arrowhead. So if there is no arrow, if just lowercase, that means this is a scalar. If we do this, that what we really mean here, we mean this is a vector. And if we do uppercase, what we mean is a matrix. Okay, so we're going to use this notation and try to rewrite the formulation we came up with using linear algebra. Okay, so using this notation, then let me introduce this. So then the vector of parameters, I'm going to show it with a vector. So that really what this means. So whenever we have theta, the vector of theta, what we mean is theta 1, theta 2, all the way to theta m, where m is the model complexity or the number of parameters that show up in the model that we have chosen. So x is often, it doesn't have to be all the training, the x of all the training data points. But you see, we can use x, which will have different points other than the data points. We'll get to that as well. And similarly, y is, here again, I'm just going to use all the data points. Okay, so, all right, so let's see how we can adopt a language, a unified language to write both of these in the same way. So the first thing we need to do is, as you see here, the basis function, for example, for the first example are like e to the power of x, and sine of x, and cosine of x. In the second example, we're just polynomials. So we have to adopt a language that is flexible enough that we can have different basis functions in them. So the way we're going to write this, any of these models, we're going to write them in this form. So let's start with that notation first. So this is still not in the matrix vector notation, but we'll turn this to a matrix vector notation. So here x, I mean x is a scalar. So it's just a number. Like I said, if I want to have x as a vector, I'll just put an arrow on top of that. But theta is a vector. So our model is not defined by just one theta. We need the entire theta vector to define the model. So now I can write these expressions. So what I want, the language I want to adopt is that call this basis, the first basis function, call that phi1 of x. And this one, phi2 of x. And this one, phi3 of x. So we have as many basis functions as we have parameters, right? So the number of basis functions is always equal to the number of parameters. Therefore, I can write this in okay, so these are the basis functions. And so that way, in this case, the basis functions are, this is the phi1 of x in this example. Phi1 of x is actually equal to 1. It's the one that is multiplied by theta 1. So in here, phi2 of x is this x. And phi3 is x to the power of 2. And I think I'm missing an x here. And so this is phi 101. This is the last basis function here of x. Okay, so for this example, m is equal to 101. For this example, m is equal to 3. But both of them are represented or expressed by this unified expansion.